To conclude this module, we're going to look at how to use the comparison test to estimate the sum of a convergent series, of course in the case where this series is convergent by the comparison test. This is something that we looked at in the case of the integral test, and we're going to take a second look at this. So let's say we are in the case where we have a series that is convergent thanks to the comparison test. That means we have a series with positive term that where we can compare term by term with a convergent series of Bn. So this series of Bn is often going to be a p-series or a geometric series, something where we can easily decide why it is convergent. So this is a setting. And in that case, when we want to approximate the actual sum of the series, the natural way to do that is to take a partial sum. So take the sum from 1 to n of the AIs, and that's an approximation. And the error we're making when we make this approximation is the nth remainder, in other words, the terms that remain if we stop the sum at n. That is, it's a sum for I equal n plus 1 to infinity of the AIs. Let's call Rn the nth remainder for the series of An. And similarly, Tn the nth remainder for the series of Bi. Then, because we have the comparison term by term, An is less than or equal to Bn for all n, we can do that for all the AIs is less than or equal to Bi for each I starting at n plus 1. And so that means that we have the same comparison between the remainders, namely that Rn is less than or equal to Tn. And Tn is something that we can often calculate in this type of situation because, as I mentioned before, the series of Bn is often going to be a p-series or a geometric series, and for these type of things we can estimate the remainder. So to control the remainder Rn, it is enough to control the larger remainder Tn. So for instance, if we want to find n such that the nth partial sum has 4 exact decimal places, when we estimate the sum of the infinite series from 1 to infinity of 1 over n to the 4th plus 5, we can proceed by comparison. Let's first look at what argument we use to justify that this is a convergent series. The general term 1 over n to the 4th plus 5 is bounded above by 1 over n to the 4th, because n to the 4th plus 5 is greater than n to the 4th, so when we divide we get something smaller than dividing by n to the 4th. And the series of 1 over n to the 4th is convergent because it's a p-series for p greater than 1. So by comparison, the series of general term 1 over n to the 4th plus 5 is also convergent. But according to what we just have seen, we can also conclude that the remainder, the nth remainder for this series, the sum of the terms of the series where the index starts at n plus 1 and goes on to infinity, is bounded above by the corresponding remainder for the series 1 over n to the 4th. So we have the sum of the terms of the form 1 over I to the 4th, where I starts at n plus 1. And this second remainder is something we can control because p-series converge by the integral test, and we have made some calculations. When we looked at the integral test, we have seen that the nth remainder is bounded above by the integral from n to infinity of the function when we have a series that is convergent thanks to the integral test. So in this case, it means that this remainder for the series of 1 over n to the 4th is bounded above by the integral from n to infinity of 1 over x to the 4th. Since an antiderivative of 1 over x to the 4th is really, well, this is x to the negative 4th, so this is an antiderivative would be x to the negative 3 over negative 3, which we can write negative 1 over 3x cubed. And we are looking at evaluating this antiderivative between t and n, and then taking the limit as t goes to infinity. When we plug t in, we get negative 1 over 3t cubed, and when t goes to infinity, this term goes to 0. On the other hand, when we plug n in, we get 1 over 3n cubed, and therefore this is our limit. And that means that our nth remainder for our series is bounded above by 1 over 3 n cubed. And now what I would like is find how many terms I need to add together in order to get an approximation of the sum with 4 exact decimal places. So I need the error, Rn, to be less than 10 to the negative 5 to make sure that the error doesn't affect the 4th decimal place. And now, once I have set up this inequality, I just have to solve for n. So that means that n cubed is greater than 10 to the 5th over 3, or in other words, n must be at least the cubic root of 10 to the 5th over 3, which is approximately 32.2. And of course here is, we're looking for the first integer where our condition is going to be satisfied. So what we have proved here is that the 33rd partial sum, s indexed by 33, in other words the sum from 1 to 33 of 1 over I to the 4th plus 5, is an approximation of the infinite sum with 4 exact decimal places. And here we don't really need to actually calculate s indexed by 33 to know that this is going to have 4 exact decimal places. If we need these 4 exact decimal places, of course, we would add together these first 33 terms. Let's look at a second example. Similar question, but now we want to know how many terms we need to add together to get an approximation with 3 exact decimal places of the convergent series from 1 to infinity of 2 over 3 to the n plus 5. So first, how do we justify that this is a convergent series? Well, we proceed by comparison because dividing by 3 to the n plus 5, I get a smaller number than if I divide only by 3 to the n. So that means that the general term of my series is between 0 and 2 over 3 to the n. And the series of 2 over 3 to the n is a geometric series of common ratio 1/2. It's 2 multiplied by 1/3 to the n. So this is a convergent geometric series because the common ratio is in absolute value less than 1. But I can also conclude not only that the series is convergent, but that the remainder for my series, the nth remainder, is bounded above by the nth remainder for the geometric series, starting at n plus 1 of 2 over 3 to the I. And this remainder for the geometric series is really the sum of a geometric series of common ratio 1/3. So what we obtain is the first term divided by 1 minus the common ratio. The first term here, because we start the series when I is n plus 1, the first term is 2 over 3 to the n plus 1. The common ratio is 1/3, so we get 2 divided by 3 to the n plus 1 over 1 minus 1/3. So at the bottom we have 2/3. So we get 2 over 3 to the n plus 1 divided by 2/3. It's like multiplying by 3/2. The 2 cancels, 1 of the 3 cancels, and we get 1 over 3 to the n. That means that the nth remainder for our series is bounded above by 1 over 3 to the n. Now what we want to do is get an approximation with 3 exact decimal places, and we can do that by making sure that the nth remainder is less than 10 to the negative 4 to make sure that we don't affect the 3rd decimal place. And this can be done if I make sure that 1 over 3 to the n is less than 10 to the negative 4, which happens if 3 to the n is greater than 10 to the negative 4, and then applying the log of base 3 function on both sides, which is an increasing function, we get that n should be at least the log of base 3 of 10 to the 4th, which is approximately 8.3. And therefore, we need n to be 9 or greater to get this accuracy, namely the 9th partial sum, the sum from 1 to 9 of 2 over 3 to the a plus 5, is an approximation of the infinite sum, which will have 3 exact decimal places. And it's time for you to turn to your homework.